Hello and welcome to this module. In this section, we are going to define normal subgroups and we will also discuss when a subgroup will be normal in G. The definition of a normal subgroup. A subgroup H of a group G is called a normal subgroup of G if AH is equal to HA for all A belongs to G. It is denoted by this notation H psi delta of G. You can just say it as H delta of G. Some of the examples here are: number 1, the subgroup of rotations in the set of all rotations Dn is normal in Dn. For any rotation R and any reflection F, we have F times R is equal to R inverse F and also R dash is equal to R dash R for any rotation R dash comma R. The second example, let us consider a group of n cross n real invertible matrices. It is denoted by G ln of R and the subgroup formed by the matrices whose determinant is 1 is denoted by S ln of R. We need to prove that S ln of R is a normal subgroup of G ln of R. Now, A inverse belongs to S ln of R for all B belongs to S ln of R, A belongs to G ln of R. Obviously, this is true because determinant A minus 1 is the same as determinant B, which is equal to 1. Hence, S ln of R is a normal subgroup of G ln of R. We shall see some results now. Result 1. Every subgroup of an abelian group is normal. Proof. Let G be an abelian group. Let us consider N to be a subgroup of G. Let G belongs to capital G. Then G n G inverse is equal to the set of all elements G n G inverse such that N belongs to N. This can be written as G inverse of N such that N belongs to N. Obviously, G and G inverse will get cancelled and therefore we are left with the set of all N such that N belongs to N, which is nothing but the set N itself. Therefore, Gn is equal to Ng for all G belongs to G, thereby satisfying the condition of a normal subgroup, and therefore N is a normal subgroup of G. Now we shall see the second result. Result 2. The center Z of G of a group is always normal. The proof. We know that Z of G is a set of all G belonging to G such that Ga is equal to Ag for all A belongs to G. Now if we take an element G belonging to Z of G, then Ag A inverse belongs to Z of G for all A belongs to G. This follows from this. But Ag A inverse is also equal to A inverse of G equal to G. Since G commutes with all the elements of G, Ag A inverse belongs to Z of G for all A belongs to G. Because of this, we can say that the center is a normal subgroup. Now, we will come to something called commutator subgroup. The definition of a commutator subgroup. Let G be any group. If A comma B belongs to G, then the commutator of A and B is the element A, B, A inverse, B inverse. If A, B, A inverse, B inverse is equal to E, then C is equal to x1, x2, so on up to xn, where n is greater than or equal to 1, where each xi is the commutator of G, is said to be the commutator of commutator subgroup. Result 3. If G is any group, then C is a normal subgroup of G. Proof. Let's assume that E can be written as E inverse and E inverse belonging to C. Now C is not equal to empty set and E is an element belonging to C. If C comma D belongs to C, because since C is a non-empty set, we can assume that there are two elements inside C. Then C is equal to x1, x2, so on up to xn, and D can be written as y1, y2, so on up to ym, because all these elements are inside the commutator subgroup. Now CD will be the product of these two elements and they belong to C. Now what will happen to D inverse? D inverse is equal to x1, x2, so on up to x inverse, and we know that when we do inversion, the xn inverse comes first. So xn inverse, xn minus 1 inverse and so on up to x2 inverse, x1 inverse. If xi is equal to ai, bi, ai inverse, bi inverse, then xi inverse is just the reverse, bi AI, BI inverse, AI inverse, which is also a commutator. The C inverse belongs to C, then C is a subset of G. When we prove this theorem, we are first proving that C is a subgroup of G, and then we are going to prove that C is a normal subgroup of G. Now we have completed one part of the proof where we have saying that C is a subgroup of G. Now to prove that C is a normal subgroup of G, let us assume that there is an element G belonging to G and C is equal to x1, x2 so on up to xn belonging to C. Then G, C, G inverse is equal to G, and instead of C we have x1, x2 so on up to xn to G inverse. Now we are going to club these elements together. So G x1 G inverse, G x2 G inverse so on up to G xn G inverse. Assume that this is equation A. We have only inserted G inverse is equal to E between xi and xi plus 1 for all I less than n. Now if xi is equal to AI, BI, AI inverse, BI inverse, then we have G xi G inverse is equal to G AI, BI, AI inverse, BI inverse, G inverse, that is equal to G AI G inverse. We are clubbing the elements together. G BI G inverse, G AI inverse G inverse, G BI inverse G inverse. Take this as equation number B. Now G AI G inverse the whole inverse will be the reverse of all these elements. So G inverse the whole inverse, AI inverse G inverse, that is equal to G AI inverse G inverse. Similarly, we can do this for BI also. Therefore, G xi G inverse is equal to G AI G inverse, G BI G inverse, G AI G inverse the whole inverse, G BI G inverse the whole inverse. Now clearly this is a commutator element. Now from equation A we have GC G inverse is a product of the commutator. Therefore GC G inverse belongs to G, which implies that C is a normal subgroup of G. Now we shall do some problems in order to understand this concept of normal subgroups even better. Problem number 1. Show that the subgroup 1 minus 1 I minus I of the group of quaternions is normal. Let's refer to the table that we have here. To the solution, now we have to prove that 1 minus 1 I minus I is a normal subgroup. So we are finding this value G1 minus 1 I minus I G inverse. Clearly, whatever be the value of G, it is going to be equal to 1 minus 1 I and minus I. For example, let's do it for one element alone. Let's take G is equal to J. Then G inverse is equal to minus J. This is from the table. J 1 minus 1 I minus I J inverse is equal to, multiply it inside and outside by these elements. Therefore, we have J. Instead of J inverse, we have to substitute minus J. So when you are doing the product inside, so it's J dot 1, J dot minus 1, so minus J, the J dot I, J dot minus J and so on. So when you do the product of all these elements, obviously from the table we get that 1 minus 1 minus K times minus J, K times minus J, which is equivalent to 1 minus 1 minus I and I. We can refer to the table and we can do this for any number of elements. We will arrive at the same result. Hence, we have verified that this is a normal subgroup. Now, let's go do one more problem, problem number 2. Let us consider a group G which is S3, the set of all permutations on 3. So, let H be the subgroup 1, 2, 3 generated by the 3 elements 1, 2, 3. So, this particular subgroup is equal to E 1, 2, 3, the permutation 1, 2, 3 and then the permutation 1, 3, 2. We have to check whether this H is normal or not. Let G be any element. So, we are assuming that it is 1, 2 and we are doing the product of this element with H. Therefore, GH is equal to 1, 2 times these elements. So, 1, 2 times E will be 1, 2, 1, 2 times 1, 2, 3 will be 1 goes to 2, 2 goes to 3. Therefore, it will be 2, 3. The second time when we are doing the product of 1, 2 with 1, 3, 2, we can see that 1 goes to 2 and 2 goes to 1 and therefore, we will arrive at 1, 3. Similarly, when we are doing for Hg also, we will arrive at the same value, that is 1 2, 2 3, 1 3, these permutations. So clearly Hg is equal to Gh, and we have proved that H is a normal subgroup. As these examples indicate, it is generally infeasible to show a subgroup is normal by checking the definition for all the elements in the group. For that, there is a test to check whether a subgroup is normal or not. The test is as follows. Theorem: normal subgroup test. A subgroup H of G is normal in G if and only if X H X inverse is a subset of H for all X in G. Proof: H is a normal subgroup of G implies X H X inverse is a subset of H A. If H is normal in G, then for any X belongs to G and H belongs to H, there is a H dash in H such that X H is equal to H dash X. Thus, X H X inverse is equal to H dash, and therefore X H X inverse is a subset of H. Conversely, if X H X inverse is a subset of H for all X, then letting X is equal to A, we have A H A inverse is a subset of H for A H subset of H A. On the other hand, letting X is equal to A inverse, we have A inverse H A inverse the whole inverse is equal to A inverse H A is a subset of H, or H A is a subset of A H. Let us verify the subgroup test for the following examples. Example 1. The group SL 2, R of 2 cross 2 matrices with determinant 1 is a normal subgroup of GLN 2, R, the group of 2 cross 2 matrices with non-zero elements. To verify this, we use the normal subgroup test. Let X belongs to GL 2, R, that is equal to G. H belongs to SL 2, R is equal to H, and note that determinant X H X inverse is equal to determinant X times determinant H times determinant X inverse, that is equal to determinant X times determinant X inverse, which is equal to 1. Therefore, X H X inverse belongs to H, which implies X H X inverse is a subset of H. However, there is an elegant way to prove normality given by the following result. For that, we should know about index. Let us see the definition of index. If G is a group and H is a subgroup, then the number of left cosets of H in G is called index of H in G and is denoted by G:H. The next result only will give an easy way to prove a subgroup is normal. Result: show that every subgroup of index 2 in any group G must be a normal subgroup. If H has index 2 in G, then G is a disjoint union of H and GH for some element G belonging to G bar H. Since G does not belong to H, Hg is also disjoint from H, and therefore Hg is equal to GH. This implies H is a normal subgroup of G. Let us see the same example but in a different way. Example: let G is equal to S3. H is equal to 1 2 3, that is equal to E 1 2 3 1 3 2. Check whether H is normal or not. Let G is equal to 1 2. We have order of G is equal to 6 and order of H is equal to 3. So, G:H is equal to 2, and by the previous result we can say that H is normal in G. Another example is alternating group. The alternating group AN of even permutations is a normal subgroup of Sn. We have the order of Sn is equal to n factorial and order of An is equal to n factorial by 2. Therefore, Sn:(An) is equal to 2, which implies An is normal in Sn. Now, let us see some theorems. Theorem: a subgroup N of a group G is normal if and only if Xn is equal to Nx for all elements X of G. Proof: let N be a subgroup of G, let X be an element of G. If Xn X inverse is equal to N, then Xn is equal to Xn X inverse times X, which is equal to Nx. Conversely, if xn is equal to nx, then xn x inverse is equal to nx x inverse. This is equal to ne equal to n, where E is an identity element of G. Thus, xn is equal to nx if and only if xn x inverse is equal to n. A subgroup n of G is normal if and only if xn is equal to nx for all elements x of G as required. The next theorem states that let n be a normal subgroup of a group G and let x and y be elements of G. Then xn times yn is equal to xyn. Proof. If n is a normal subgroup of G, then ny is equal to yn, and therefore xn times yn is equal to x times ny times n, that is equal to x times yn times n, which is equal to xy times nn. But nn is equal to n since n is a subgroup of G. Therefore, xn times yn is equal to xy times n as required. Let us see the next theorem. Let G be a group, let H be a subgroup of G, and let n be a normal subgroup of G. Then the set Hn is a subgroup of G where Hn is equal to the set of all elements Hn such that H belongs to H and n belongs to n. Proof. The set Hn clearly contains the identity element of G. Let x and y be elements of Hn, we must show that xy and x inverse belongs to Hn. Now x is equal to hu and y is equal to kv for some elements h and k of H and for some elements u and v of n. Then xy is equal to hk k inverse ukv, but k inverse uk belongs to n since n is normal. It follows that k inverse ukv belongs to n since n is a subgroup and k inverse ukv is the product of the elements k inverse uk and v of n. Also hk belongs to H. It follows that xy belongs to Hn. We must also show that x inverse belongs to Hn. Now x inverse is equal to u inverse H inverse, that is equal to H inverse times hu inverse H inverse. Also H inverse belongs to H since H is a subgroup of G, and hu inverse H inverse belongs to n since n is a normal subgroup of G. It follows that x inverse belongs to Hn and thus Hn is a subgroup of G as required. Let us see what condition Hn will be a normal subgroup. Theorem. If n is a normal subgroup of G and m is a normal subgroup of G and mn is equal to the set of all elements mn such that m belongs to m and n belongs to n, prove that mn is a subgroup of G and that mn is a normal subgroup of G. Proof. Let m1, m2 belongs to m and n1, n2 belongs to n. m1 n1 the whole inverse times m2 n2 is equal to n1 inverse m1 inverse m2 n2, which is equal to n1 inverse m1 inverse m2 n1 n1 inverse n2. Here n1 inverse m1 inverse m2 n1 belongs to m and n1 inverse n2 belongs to n, so that m1 n1 inverse m2 n2 belongs to mn. This shows that mn is a subgroup of G. Let m belongs to m and n belongs to n. Since m and n are normal subgroups of G, this implies that Gm G inverse belongs to m and Gn G inverse belongs to n, so that Gmn G inverse belongs to mn. This shows that mn is a normal subgroup of G. We know that the intersection of subgroups form a subgroup. Do you think it is true for normality also? Let us verify. Theorem. The intersection of a family of normal subgroups is a normal subgroup. Proof. Let G be a group and let HA, where A belongs to H, be a family of normal subgroups of G. Let H be equal to the intersection of all A belongs to A, HA. We want to show that H is a normal subgroup of G. Since the intersection of a family of subgroups is a subgroup, it remains to show that H is normal. Let G belong to G and let H belong to H. I must now show that GH G inverse belongs to H. Now, H belongs to H implies H belongs to HA for all A. So, since H is a normal subgroup of G for all A, GH G inverse belongs to HA for all A. Therefore, GH G inverse belongs to the intersection of all A belongs to A, HA, which is equal to H. Therefore, H is a normal subgroup. What are the trivial non-normal subgroups of a group G? The following theorem will state that let G be a group, then the singleton set 1 and G are normal subgroups of G. Proof: to show that the singleton set 1 is normal, let G belongs to G. The only element of 1 is 1 and G dot 1 dot G inverse is equal to 1, which belongs to the singleton set 1. Therefore, the singleton set 1 is normal. To show that G is normal, let G belong to G and let H belong to H. Then GH G inverse belongs to G because G, H and G inverse are all in G and G must be closed under its operation. This implies that G is normal in G. These are trivial non-normal subgroups of G. In the previous module, we have seen about homomorphism, automorphism and inner automorphism. Here we are going to see how these are related with the normal. Theorem: let G and G dash be groups and phi be a function from G to G dash and also a homomorphism. Then kernel phi is a normal subgroup of G. Proof: let H is equal to kernel phi. We already know that H is a subgroup of G, so it suffices to check normality. So take any H belongs to H and G belongs to G. By definition of the kernel, we have phi of H is equal to E dash, which is the identity element of G dash. Hence, phi of G H G inverse is equal to phi of G times phi of H times phi of G inverse, which is equal to phi of G times E dash times phi of G inverse, which is equal to E dash. Therefore, GH G inverse belongs to kernel phi, which is equal to H. This implies that H is normal. In this module, we have seen about normal subgroups, the various properties of normal subgroups, commutator subgroups, and also the various theorems to identify normality in subgroups. I hope this was useful to you. Thank you.